We have the three use cases that three of the companies will be sharing. I would like to invite Prasad Panchangam, founder CEO of CloudXIM.
Hello, thank you. Thank you. Hello, everyone. Can you hear me? Okay. My name is Prasad Panchangam. I have a consulting business called CloudXIM Technologies, but I have now been, for the last few months, involved with starting a company in the AI edge processing space, particularly silicon. So I'm a silicon guy, and I'm going to sort of give you a silicon flavor for AI edge processing. And I was originally scheduled to be on a panel at 2 o'clock, but then we kind of swapped, and I'm doing this presentation. This is my agenda. It's an incredibly ugly slide, but essentially what I'm trying to say here is I'm just going to quickly go through the background and context of what I'm going to say, because that's really important. You need to understand, what algorithms I'm talking about, what specific aspect of the ecosystem I'm talking about, and so on. And then there's current products. I'd like to quickly cover that. Most people look at the edge in different ways, look at AI in different ways. So I'd like to set that stage. And then I want to cover the challenges that we in New Netra are trying to address. And then I'd like to give you, a little bit of a view into what the core offering is and what we're trying to do. So my background is primarily in chips and systems. I was a senior director of technology at AMCC, doing all of the ARM64 stuff for the data center, SoC. That's now been called Ampere. It got acquired by Ampere. I was at Microsoft for several years, doing a lot of the media SoCs that, we actually pioneered a lot of the IPTV set-tops and so on. So I'm very familiar with, general purpose CPUs, DSPs, fixed state machine accelerators, and so on. So when I go through this presentation, I'll sort of touch upon all of these things. So first thing is this big slide. Everybody knows this, right? So if you look at a lot of AI today, almost literally 90% of it is done in the cloud. So you have offerings from Google, you have offerings from Microsoft, you have offerings from Facebook, you have a lot of these guys who run a lot of classification, object classification, face recognition, and so on in the cloud. There's also a lot of devices, embedded devices that you see in the home today that essentially connect to the cloud and do a lot of recognition there. So you'll see, if you go to one of these Chinese shows where they sell all these devices, every one of these devices will have some cloud connectivity to connect up to the cloud and be able to recognize objects and so on. But there is a definite push to move all this intelligence, not all of it, but at least the inferencing part of it from the cloud into devices at the edge. And obviously, these are at the bottom, you'll see what the benefits of this are. First is obviously latency, right? If you want to send something to the Google Cloud, the round trip time might be 300 milliseconds. It might take you several seconds for you to recognize an object, which is probably a non-starter for the use case. There's also low power because, you need a lot of power to power up the radio, push data up to the network, and, a per inference power footprint is going to be high because you're going to do all this in the data center, which is all running on, high power hardware, has a lot of HVAC and so on. So power per inference is very high. So low cost, obviously, again, every time you access the Google service, you have to pay for it. It's not free. So Google essentially amortizes their CPU cost to you. And then privacy, obviously, because every time you take somebody's picture and push it up into the cloud, it's a privacy concern. So because of all of these reasons, there's a definite push to the edge. Now, before we launch off into what it is that edge is all about, AI means different things to different people. I just took this picture from a McKinsey report. They have a whole spectrum of techniques, from traditional techniques to advanced techniques. And you'll see that AI is essentially a vast space. Everybody is confused about it. Everybody thinks AI means feed-forward neural networks. That's not true at all. AI, or data science, as some people like to call it, a naive base classifier is also AI. So in this presentation, I'm not going to be talking about any of these things at the bottom. Modern vision use cases like recognizing somebody's face, recognizing an object, figuring out somebody's speech pattern, figuring out what text can be represented for a particular spoken word, and so on, don't use any of these techniques. Most of them use what are called convolutional neural networks, and a lot of new techniques called recurrent neural networks are coming up, particularly for speech, because you need to have some memory of what was said before you can classify something that is being said. So there's a lot of recurrent and convolutional neural networks that is forming the bulk. So, our colleague from ST just talked about, all of these networks. They're all convolutional neural networks. So doing things like pooling, adding sigmoids. So whenever you look at a TensorFlow script, when you see adding convolutional layers and max pooling layers and sigmoids, they all refer to convolutional neural networks. So for the purposes of this presentation, that's all I'm going to talk about. Transfer learning and reinforcement learning, not as much, because they cover a lot of training aspects, and I'm not going to be discussing training. That's the other thing I'm going to say. At the edge, people usually do inference. So you've got to understand the difference between inference and training. Inference is you have a trained model, you look at a real-world signal coming in, and you predict or classify what that is based on the model you already have. Training is creating that model, which is a much more CPU-intensive effort, and it's looped multiple times, and so most of that is done by big NVIDIA GPUs in the cloud. So general-purpose GPUs do a lot of the training in the cloud, but what we're going to talk about is inference. So here, the definitions for this presentation, AI in my dictionary for the purposes of this presentation is deep learning techniques using ANNs, and they can be used to solve a variety of problems. And in terms of the techniques, I am not going to talk about SVMs and linear regression and all that. I'm just going to talk about classification and continuous estimation. Again, this is most widely applicable for the edge, because today's edge, as you'll see later on, is mostly about vision, camera use cases, speech, text, healthcare, where you figure out something from the signal and so on. So, we are talking about a very narrow set of AI techniques and AI algorithms, but for the purposes of edge and IoT, this is what we should focus on. And again, the focus again is on feed-forward neural networks and recurrent neural networks and CNNs. And what McKinsey says is just these three techniques enable somewhere between 3.5 to 6 trillion worth of value. So that just gives you an idea of how much of money is behind AI and particularly these techniques. So again, I just wanted to put this up here just to give you an idea. Just look at the top two. Problem types of classification and continuous estimation. So everything from security cameras and drones and wearables and medical devices, smart speakers, head-mounted displays. Think of anything you want, they all fall into the first two things. So that's where the maximum value is, and that's where all the money is going to make silicon and so on. All right, so let's look at the edge. What do we have at the edge? Current products, right? So edge IoT means what? So I want to cover smartphones first, because this is where the bulk of the volume is. This is where the bulk of the investment is. And if you look at this space, you'll be blown away, because every one of the big guys has invested literally hundreds of millions of dollars to put what they call neural engines into their smartphones. So if you have one of these Apple phones, 7 plus and above, you probably have an A11 or A12 chip. They call it the bionic chip. It's a really nice marketing term for something that has an integrated inference engine. So all of these are inference engines. You don't train networks on a smartphone. You inference from a real-world picture, trying to classify what this picture is. So the Galaxy S9 has a neural engine from DeFi. DeFi essentially is now owned by Xilinx. They sold themselves to Xilinx, and it's part of the Xilinx suite, ML suite. So the Chinese guys have, the Huawei, and there's MediaTek. MediaTek has an engine from Cadence. Cadence acquired Tensilica. Tensilica has a neural network processor. So if you look at all of these guys, they have pretty large, neural network accelerators on their SoCs. And when I say pretty large, these are large in terms of area, in terms of energy, in terms of bandwidth. I mean, the system data bandwidth that something like a Cadence P6 requires is something like LPDDR4 bandwidth, something like 10 gigabytes to 20 gigabytes per second. So these are all big engines that run on all of these things. But you'll see that there is, a big trickle down of these engines to mid-tier phones. So you don't have to buy the most expensive phone to get these things. They're all coming down into cheaper and cheaper phones. So this should give you an idea that, edge, a smartphone is really at the edge of the network. There's a lot of, investment in, AI that's going into these. Now, why would you even need an accelerator for some of these things? I mean, some people may have, may think that why can't they just run all this on the CPU? I mean, CPUs, general purpose CPUs, unfortunately, don't have this kind of efficiency as a fixed state machine accelerator to do neural network applications, to run the mathematical operations. If you look at a convolutional neural network, every convolutional layer is a multiply accumulate. And a fixed state machine accelerator simply has 10x, maybe 20x more efficiency than a GP CPU to be running all of this stuff. So there is a huge market for people building accelerators to go into these things. So this is sort of the table stakes for smartphones. So what about IoT? I mean, this conference is all about IoT. So what has happened is that today, essentially, you see three things that are driving a lot of AI. There's voice assistants, which is all your Alexa and Siri and OK Google and all of these, Cortana and all of these guys who need to be able to recognize your voice and figure out what is it that you're saying and be able to execute an action. So voice assistants have driven a lot of IoT. And again, today, if you buy a smart speaker, it's most likely going to be connected to the cloud, right? Siri on my iPhone doesn't work if I'm not connected to the cloud. But there's a huge push to move a lot of this onto the edge so that it doesn't have to connect to the cloud. So this is going to translate into the bottom panel here, which is, as this intelligence moves into the edge, then, things like industrial IoT and consumer IoT, like wearables and video doorbells and smart homes. Video doorbells is a huge use case in the US. I don't know if you know this, it's kind of funny, but Amazon really loses a lot of money in people stealing stuff from other people's homes. So an Amazon guy comes, brings a package, drops it on your porch, goes off, you're not at home, somebody else comes, picks up the package, is gone, right? So Amazon essentially loses a lot of money there. So they're investing in a camera, a smart camera that's on the door, and if the Amazon delivery guy shows up, the camera looks at that guy and says, oh, this is the Amazon delivery guy, and opens the door. And the guy drops, or he opens a small side door, like, the door that the dog goes through, so that he can just drop the package in through that. So it's a big deal. Video doorbells are big deals. So this is where we are getting to. And there's a huge push now. There's a huge amount of investment in consumer IoT and wearables, right? I mean, every one of you who has one of these things, it's getting smarter and smarter, right? I mean, you have a Series 3 or a Series 4 watch, you walk 20 steps, all of a sudden it knows you're walking. It says, hey, shall I turn on the workout app? So today you have a Series 4 watch, it looks at your ECG and says, you're probably having some sort of, atrial fibrillation or something like that. So these things are getting smarter and smarter. And going forward, there is going to be a lot of push in this space. I want to talk about smart cameras, right? So I don't know whether you guys know this. In China, there are literally 300 million smart cameras. They look at everything. They look at kids in the school. They look at whether the kid is happy or not. They look at your car. They look at where you're going. You show up in China, you go through immigration, and then there are like millions of cameras tracking you. Where are you going? What are you doing? It's crazy. It's unnerving, but they have it. right? This is a picture. You can actually see a whole bunch of cameras looking at a scene of people. They're classifying every person's face in that scene. They're looking at every vehicle that's on the road. And they're actually going to go to 400 million cameras now. I mean, it's like a gigantic spider-like, country with like octo eyes everywhere. So there's a huge market for surveillance, obviously, and cameras and vision and figuring out what is in the scene is a huge deal in AI. And this is what is driving a lot of edge IoT smartness, if you will. So there's a lot of Chinese chip makers, right? There's Cambricon, there's HiSilicon, Horizon Robotics, Kendrite, all of these guys who are building, and there's almost a dozen more startups in the Beijing and Shanghai regions that are building all of this stuff. And Intel is, I just put Intel up here, but FlexLogix has a part, and NVIDIA has a part. Every one of these guys have a part. And there's companies like Simple Machines and Wave Computing. All of these guys are building parts. But what I want to point out here is that custom hardware enables much more complex deep neural networks than a CPU can handle. So smart cameras is probably going to be the biggest driver of fixed state machine accelerators than anything else, because vision, the vision use case is probably the biggest. And our colleague from ST talked about the drip bottle. That's a vision use case. You look at the bottle, figure out how much there is in, how much fluid there is in it. So this is one thing I wanted to talk about. Now this is where we get down to the bottom end, right? IoT sensors. Now what is it that we can do in IoT sensors? A person walks around with a Holter monitor, right? You have a little device that you put on your chest. It runs for a week, and then it collects data. You take it back into the hospital. They hook it up. That it sucks out all the data from the flash in there, and then a report is generated by how much of arrhythmia they see in 48 hours, 96 hours, 1 week, whatever. But the real clinical demand in that market is don't come back after 1 week. If you're having an episode while you're wearing it, we want the device to know, and we want the device to flag it. So there's a lot of intelligence that needs to get on sensors, on body, and into the sensor. So you have these really tiny microcontrollers, and if you can't have like a Cortex A9 or a 64-bit ARM core or like an x86 big core be very inefficient at processing deep neural networks, what can you do on a Cortex M series or a Cortex A series processor, right? So ARM has its own strategy. They're coming up with something called Helium, which is their instruction set extension for AI edge processing. But they have a Cortex M system software interface spec. They have neural network extensions to it, and you can port your DNNs to it. But then there's other companies, right? There's Sentient, which is trying to build an analog, what they call a neural processor. Then there's Greenwaves, there's Eta Compute, and there's a lot of these guys that are trying to build processing capability for these sorts of devices. So quickly, what's the challenge that we are trying to address? So I just kind of gave you a landscape. There's smartphones at one end of the spectrum, there's cameras, and there's edge IoT devices. But if you look at a system designer, what is it that they really want, right? A vendor needs a path from a data spec to a product, right? If you go to a systems guy who says, I have data for my use case, now I want to build a product for it, right? So you can't just say, okay, here's a little chip, go build your thing on it. They just don't have the smarts for it. Nobody has big, deep, data science teams to do all of this stuff. The second thing is, you need to have the flexibility to choose between different platforms. Do I want to run this on an existing ASIC? Do I want to run this on the CPU, on a Cortex M series processor, or the STM32 part that our colleague just talked about? Do I want to run this on a tiny lattice FPGA that goes into my device? I think you guys know this. All the iPhones have a lattice chip in it, right? They all. So whenever you say Siri, it says it's the lattice part that actually wakes up. It's asleep. It wakes up on that little Siri thing, and then it wakes up the rest of the phone. So there is a part in there. So so you need to have the flexibility. And chip designers need a tool to generate a processing engine from different model parameters. So if I have a model, how do I know what capability, what sort of capability, processing capability I need? And then you need area and performance optimized IP. So this is where we sort of come in. So what we are saying we are going to do is we're going to create a tool which we call the New Netra Design Studio that will essentially take a model and a weights file essentially that's provided by the customer and turn it into IP, soft IP that you can put into an ASIC. So we can do FPGAs, we can do microcode that goes onto a Myriad X if you want, or on a Jetson Nano, or we can do synthesizable RTL that goes into. Sorry, I'm completely out of time, but if you have any questions, I'll be happy to answer it. That's all I had anyway. This is the value prop that we're saying we're going to bring to the table. But if you have any questions, I'd be happy to answer it.
Thanks, Prasad. Thanks, Prasad.
Right.
Please give him a big hand. We'll just wait for a minute. Can I have Arul Arya, IASI, to come and hand over the memento, please? Good work. Excellent. Excellent.
Thanks a lot.
Thank you.